Hello, I'm Shinpei Shina, a student at the University of Tokyo. Today I'm going to introduce our paper, Lightweight Preemptive User-Level Threats, which investigates preemption techniques for user-level threats. Let me first describe the motivation of this work. In various situations, more threads than the number of cores are created. For example, if a parallel program calls some external libraries and the library is also parallelized, there is nested parallelism. In nested parallelism, the number of threads grows exponentially as the nesting level increases. In addition, asynchronous tasks can be created dynamically, and they are often represented as threads. So, efficient thread schedulers for handling these many threads are needed. Today, software stacks of applications are often complicated, and many parallel libraries are hierarchically composed, yielding nested parallelism. Also, in complicated situations like in situ analysis, various kinds of tasks coexist, creating many threads. Therefore, it is important for the thread schedulers to be able to efficiently handle many and fine-grained threads, so lightweight thread implementations are required. In addition, customizing thread schedulers for specific workloads is often beneficial. Because two general thread schedulers do not perform well in some situations, it is important to design thread schedulers for specific workloads by utilizing some application hints. For example, locality-aware scheduling for memory-bound applications and priority-based scheduling have been intensively studied until now. This example shows a priority-based scheduling with work steering strategy. There are low priority threads and high priority threads, and they are separately managed by thread queues. A core first tries to pop a higher priority threads from its own thread queue, and if no thread exists, it then tries to steal high priority threads from others. Low priority threads are scheduled when high priority threads are not found. It is desirable for the application programmer to customize these thread schedulers for their own needs, especially for complicated softwares. In situ analysis is a good example in which high priority threads and low priority threads coexist, and high throughput of computation is important. And in this work, we focus on end-to-end threads or user-level threads, which are lightweight and flexible thread implementation. One-to-one threads or kernel-level threads are threads controlled by the OS kernel, and widely used pthread and OpenMP threads implementations are based on one-to-one threads. However, one-to-one threads are insufficient for thread scheduling for high performance because of their heavyweight threading operations such as thread creation and context switching. They are heavyweight because they involve context switching to the kernel space, which consumes many CPU cycles. The scheduling policy of one-to-one thread is also inflexible because the user cannot customize thread scheduling policies in user space. On the other hand, end-to-end threads are promising because of their lightweight threading operations and flexible scheduling policies. Because of these benefits of end-to-end threads, many parallel runtimes have adopted end-to-end threads as their threading layer. However, end-to-end threads have some downsides, and one capability that end-to-end threads are missing is preemption. Lack of preemption can be problematic in many situations. For example, priority of threads can be ignored without preemption. The figure shows that a low priority thread is occupying this core for a very long time, and high priority threads are waiting for it. In this situation, the thread scheduler has no way to remove the low priority thread from the core unless the thread voluntarily yields the core. If the thread scheduler has the capability of preemption, the low priority thread can be immediately evicted from the core once high priority thread becomes ready to run. Another issue caused by lack of preemption is the deadlock issue. The problem is that Many existing multi-threaded programs assume that they can exclusively use all of the cores, and thus they sometimes have their own thread synchronization mechanisms, such as thread barriers based on busy loops or spinning. When they run over non-preemptive end-to-end threads, and there are more threads than the number of cores, deadlock occurs. And in this figure, these threads are waiting for other threads in busy loops, but the thread scheduler does not have a chance to schedule other threads because running threads are spinning on the cores. If we have preemption, the deadlock issue would be resolved. Thus, in this paper, we investigated preemption techniques for end-to-end threads. Here's a summary of contribution of this paper. First, we investigated preemption techniques for end-to-end threads, which can be implemented in a pure threading library so that they can be used from C or C++. Specifically, we investigated two preemption techniques. Signal yield is an existing technique, but we found it was insufficient, so we proposed KLT switching for safe preemption. We also proposed several optimizations for preemptive end-to-end threads based on the detailed performance analysis. Finally, we implemented preemptive end-to-end threads on AlgoBots, a lightweight end-to-end threading library developed at Argonne National Laboratory, and we evaluated the performance on various benchmarks and applications. We found that preemptive end-to-end threads can be as fast as non-preemptive end-to-end threads in practical settings. Alright, so here is an outline of today's talk. First, I will introduce a one-to-one threading model and end-to-end threading model, and explain the design of preemption techniques for end-to-end threads. After that, I will talk about some optimizations, evaluation, and conclusion. Alright, so basically, there are two threading models, one-to-one threading model and end-to-end threading model. In one-to-one threads, threads visible to the user are directly mapped to kernel-level threads. So one thread corresponds to one kernel-level thread. Most of today's pthreads and OpenPthread implementations are based on one-to-one threading model, even though the specification does not require it. Sometimes one-to-one threads are simply called kernel-level threads. On the other hand, in end-to-end threading model, a thread visible to the user does not correspond to one kernel-level thread. In end-to-end threading model, many user-visible threads are created, and they are dynamically mapped to kernel-level threads by context switching them in user space. Usually, as many kernel-level threads as the number of cores are created at the beginning of execution, and many user-level threads are dynamically created. End-to-end threads are often simply called user-level threads. As I mentioned earlier, end-to-end threads have many benefits like lightweight threading operations and customizable scheduling policies, but most end-to-end thread implementations do not support preemption. Basically, preemption for kernel-level threads is usually supported by the kernel. Therefore, one-to-one threads are preemptive because they have one-to-one mapping to kernel-level threads. However, end-to-end threading model is not preempted by the kernel, so in naive implementations, end-to-end threads are non-preemptive. In non-preemptive end-to-end threads, threads have to call explicit yield functions for context switching to others, and we will investigate threading techniques for achieving implicit preemption for end-to-end threads. And we will investigate two preemption techniques, signal yield and KLT switching. The first technique is signal yield. Signal yield has been previously investigated in some papers, and recently it was adopted by the Go language. I will explain the basic working of signal yield, and the basic idea is to interrupt the execution of threads by using a signal issued by some system calls, and then yield within the signal handler. This figure shows the timeline of thread execution. And thread 1 is running on KLT1, a kernel level thread. Now thread 1 is interrupted by a signal and a signal handler is called. We can use a timer signal for periodic interruption. And then within the signal handler, thread 1 performs context switching to the scheduler context. The scheduler arbitrarily chooses the next thread to run on KLT1, and the scheduling decision is based on the scheduling policy provided by the user. Eventually, as thread 1 is rescheduled by the scheduler, and the execution context is switched from the scheduler to the signal handler in thread 1. Then we just exit the signal handler and continue the remaining execution from here. Okay, so signal yield is a very simple and straightforward way to realize preemption for end-to-end threads. But in practice, it has a safety issue, and we call it KLT dependence issue, and I will explain it. The fundamental problem is that some existing library functions can directly access KLT local data, but not end-to-end thread local data. This is because modern operating systems like Linux do not provide first-class support for end-to-end threads. For example, glibc malloc uses KLT local caching by using KLT local data or thread local storage in some other words. This causes a KLT dependence issue, and let me explain the KLT dependence issue using this figure. And in this figure, thread 1 is executing malloc, and a signal is delivered while executing malloc. And then the execution context is switched from thread 1 to thread 2 in the same KLT1. If thread 2 also calls malloc, a problem happens. In this execution flow, malloc is called during the execution of another malloc within the same KLT. Because malloc directly accesses KLT local data, but not end-to-end thread local data, both of the malloc executions accesses the same KLT local data of KLT1. From the point of view of KLT1, malloc is concurrently called, and multiple contexts concurrently accesses the KLT local data. So there is less condition for the KLT local data, which causes an undefined behavior and program may crash. Then how can we support self-preemption for end-to-end threads? The KLT dependence issue arises because KLT local data are assumed to be accessed sequentially, but signal yield breaks this assumption, causing less condition for the KLT local data. The solution for this issue is to switch to another kernel level thread when preemption happens, so that KLT local data are not modified while a thread is being preempted and suspended. And we call this novel technique KLT switching. And here is how KLT switching works. The idea is to switch to another KLT only when preemption happens, so that KLT local data are not modified while being preempted. In this figure, thread 1 is running on KLT1, and it is interrupted by a signal as well. In the signal handler, KLT1 wakes up another kernel level thread, KLT2 in this case, and the scheduler is invoked on KLT2. KLT1 suspends its execution by using some system calls, waiting for thread 1 to be rescheduled by the scheduler. And later, other end-to-end threads are scheduled on KLT2. As long as preemption does not happen, end-to-end threads are scheduled on the KLT2 in the same way as non-preemptive end-to-end threads. Even if end-to-end threads on KLT2 access the KLT local data, it is KLT local data of KLT2, and KLT local data of KLT1 is not modified. Once preemption happens, an end-to-end thread is associated with the KLT and saves the state of the KLT local data until it is rescheduled. Eventually, thread 1 is rescheduled by the scheduler. At that time, KLT2 wakes up KLT1 and starts to sleep again, Then KLT1 is now active and exits the signal handler and continues to execute the remaining execution from here. Okay, so in KLT switching, many kernel-level threads can be created. Here I show the generalized thread mapping in preemptive M10 threads. A worker is virtualization of a physical core. And in traditional M10 threads and signal yield, a worker corresponds to one kernel-level thread. But in KLT switching, a worker does not have one-to-one mapping to kernel-level threads. KLT switching can use many kernel-level threads, but only the same number of KLTs as the number of workers are active at the same time. Therefore, the scheduling policy of KLT switching threads can be fully controlled by the user. Then I briefly introduce optimization for preemptive M10 threads. The first optimization is about the preemption timer. Preemption timer is a periodic timer interruption for each worker. We observed that naive implementation of preemption timer is not scalable because when signals are delivered at the same time across different cores, very large amount of time is consumed because of lock contention in the kernel. So we proposed an optimization for it by aligning timings of interruption so that interruption is not overlapped across cores. After applying this optimization, the preemption timer becomes scalable enough and the cost of interruption across cores are almost constant. Another optimization is for KLT switching. There are two optimizations for KLT switching, and the first optimization is about suspending and resuming KLTs. By utilizing few texts provided by Linux rather than using POSIX functions, the performance of KLT switching improves. The POSIX functions incurs higher overheads because of additional signal handling. The second optimization is worker local pools for suspended KLTs. Like memory management like Linux, we can consider worker local caching for KLTs. It has an advantage in avoiding resetting CPU affinity of KLTs, reducing the number of system calls. When KLT is remapped to the worker, the CPU affinity of the KLT should be set to the CPU, which the worker is mapped to. When the KLT is remapped to the same worker, we can skip resetting CPU affinity for the worker, reducing the KLT switching's cost. Before we move on to the evaluation, so we summarize thread implementations here. We addressed 4 types of threads: one-to-one threads, non-preemptive M10 threads, preemptive M10 threads with signal yield, and preemptive M10 threads with KLT switching. First of all, explicit threading operations such as thread creation and synchronization among threads are heavyweight in one-to-one threads, whereas M10 threads have lightweight threading operations regardless of whether they are preemptive or not. The absolute overhead of preemption of M10 thread is larger than that of one-to-one thread, and the cost of KLT switching is much higher than that of signal yield. And all of the M10 threads have the capability of customizing thread schedulers in user space. And signal yield is not safe preemption. And one downside of KLT switching is its high overhead of preemption, but it is acceptable because preemption is infrequent enough in practice. Then we will move on to the evaluation. In the evaluation, so we used 2-socket Intel Skylake processors, and there are 56 cores in total. We implemented the preemption techniques, signal yield, and KLT switching on Argobots and M10 threading library. I will first talk about evaluation with a micro benchmark to measure the overhead of preemption. Then we will show that preemptive M10 threads can resolve the deadlock in nested parallelism and outperforms one-to-one threading model. The last evaluation is in-set analysis with ramps to show the benefit of customizable schedulers with preemption. Okay, so first, we measured the overhead of preemption. The figure shows the additional overhead relative to the baseline execution of non-preemptive end-to-end threads. We change the timer intervals, which are shown in x-axis. First of all, the overhead of KLT switching is much improved after applying several optimizations, and the overhead of KLT switching is still much higher than that of signal yield, but we consider the overhead of KLT switching is acceptable. When the timer interval is 1 millisecond, the overhead of KLT switching is only about 1%. Considering that the OS preemption interval is typically in the millisecond range, the overhead of KLT switching is still less than 1% in practical settings. Next, evaluation of nested parallelism with Koreski decomposition. In this application, there are two levels of parallelism, outer parallelism and inner parallelism. The outer one is parallelized by OpenMP tasks with data advantages among submatrices, and inner parallelism exists within the inter-MKL plus library. As I mentioned earlier, this situation can cause deadlock without preemption because inter-MKL uses busy loop-based barriers for thread synchronization for the sake of performance. When running this application over non-preemptive end-to-end threads, deadlock occurs. By introducing preemption to end-to-end threads, Koreski decomposition can run over lightweight end-to-end threads. We use the Bolt, an OpenMP wrapper over Algobots as an end-to-end thread-based parallel runtime. For the purpose of evaluation, we reverse engineered inter-MKL and replaced busy loop-based barriers with the barrier implementation provided by the end-to-end threading library. It is just a hack for evaluation only, and preemptive end-to-end threads based on KLT switching can run even without this hack. For comparison, we also evaluated Intel OpenMP, which should be the default parallel runtime based on one-to-one threading model. We also evaluated the flat version of Intel OpenMP with the inner parallelism disabled, which is often common practice. Looking into the result, when the problem size is small, flat version does not perform well because the outer parallelism is not enough to utilize all of the cores. Non-preemptive bolt performs the best thanks to the reverse engineering hack, and preemptive bolt performs close to the non-preemptive one, incurring a little overhead of preemption. The performance of Intel OpenMP with nested parallelism is not good because of heavyweight threading operations of one-to-one threads. The final evaluation is in-situ analysis with LAMPS, a widely used molecular dynamics simulator. In-situ analysis is a modern way to perform analysis and simulation at the same time in memory to reduce the total I/O cost. In this evaluation, we create analysis threads and simulation threads, which can be executed asynchronously. Because analysis threads are created based on the progress of simulation threads, the analysis threads should have lower priorities than simulation threads. And in this case, preemptive scheduling is beneficial to evict lower priority threads in favor of higher priority threads. And this is a result of evaluation of in-situ analysis. The line plot shows a relative overhead compared with the baseline, in which only simulation is conducted without analysis. Thus, the relative overhead represents the additional overhead caused by analysis threads. The result shows that preemptive M10 threads perform the best because of the lightweight threading operations of M10 threads and efficient priority-based scheduling enabled by preemption. Finally, I will summarize this work. We have investigated two preemption techniques for M10 thread, signal yield, and KLT switching. We also implemented these preemption techniques on Algobots and evaluated their performance with detailed analysis. In the evaluation of core key decomposition, our preemptive end-to-end threads can avoid a deadlock and outperform the Intel OpenMP based on one-to-one threads. The evaluation of in-set analysis shows that preemptive user-defined schedulers specialized for specific workloads are beneficial. Summarizing, preemption brings more freedom to end-to-end threads in implementing efficient user-defined schedulers with low overhead. Thank you for listening.